Hey everyone, and welcome back to the podcast. I'm Mark.
And I'm Jenny. So Mark, I've been hearing whispers, some really intriguing tech talk, about a future of computing where noise is a good thing. That feels a bit upside down from what I know about tech.
Oh man, this is the cool part. You're talking about probabilistic computing. It's this emerging paradigm that's built on randomness, or more specifically, controlled noise. We're not fighting it anymore, we're collaborating with it.
Controlled noise? That does sound like a contradiction. We spend so much time trying to eliminate noise in technology. Static on the radio, glitches in a video feed. How can it possibly be useful for serious computation?
Right? Isn't that wild? But here's the thing about probabilistic computing. Instead of trying to force bits into a deterministic 0 or 1 like classical computers, it uses what are called p-bits. These p-bits actually times leverage times thermal fluctuations, that natural noise, to jump between states.
Okay, wait, let me get this straight. So, a classical bit is always a fixed 0 or always a fixed 1. A quantum bit, a qubit, can be both at once thanks to that weird quantum property, superposition. And a pa-bit, it's kind of like flipping a coin really, really fast, all the time?
Yes, precisely. Think about it this way. A p-bit isn't a fixed value at any single moment. It fluctuates between 0 and 1 over time due to that thermal energy. But the probability times of it being in either state at any given instant or over an average can be meticulously controlled. This allows it to model uncertainty directly, which is quite significant for certain kinds of problems.
Okay, that's fascinating. My brain is definitely doing a little flip-flop with the p-bits concept. But how is this useful in a practical sense? And where does this energy efficiency part come in? I heard some claims that sound almost too good to be true, honestly.
Oh, the potential energy efficiency is where things get especially interesting and, frankly, crucial in today's world. One of the major reasons probabilistic computing is gaining traction is its potential for ultra-low power consumption. Because these systems are designed to use natural physics, like thermal noise, which is always present, they can perform computations with significantly less energy than traditional deterministic systems that constantly need energy to maintain clean, stable states. The core idea is that by working times with the randomness rather than constantly expending energy to fight it, you can save a substantial amount of power.
So instead of brute-forcing calculations with a lot of energy, you're sort of nudging a system that's already naturally fluctuating and leveraging that inherent movement to do the work?
That's a good way to see it. It's connected to something called thermodynamic computing, too. These systems use entropy-driven operations, basically leveraging the natural tendency of systems to move towards disorder, but in a carefully controlled and useful way, to perform computations. Early analysis suggests the potential for massive energy savings, especially when tackling highly complex optimization problems that currently consume significant computational resources.
That's a different way of thinking about computation, truly. It almost feels more organic, more aligned with how physical processes happen in the universe.
Right? Isn't that cool? And here's another interesting point. These p-bits have a potential near-term advantage over quantum computing when it comes to implementation. They can actually be implemented using existing semiconductor technologies, like magnetic tunnel junctions, or MTJs for short, and even some standard CMOS circuits. This means probabilistic computing could have a quicker path to real-world application, because it can be built on established manufacturing processes, avoiding some of the extreme environmental requirements quantum computers currently face.
Okay, that makes sense. So potentially a quicker path to seeing these systems in action compared to quantum computers, which need these super cold environments and specialized fabrication. But what kind of problems are these p-bit systems particularly well suited for solving?
They're particularly good at what we call NP-hard problems. These are the kind of problems where the number of possible solutions grows very, very quickly with the size of the problem, making finding the optimal time solution practically impossible for classical computers in a reasonable time frame. Think complex optimization tasks in logistics or supply chains, sophisticated financial modeling, drug discovery simulations, some areas of artificial intelligence specifically involving inference. Problems where finding a near-optimal or most probable answer is more feasible than searching for one perfect, deterministic outcome.
Like figuring out the most efficient delivery routes for a huge fleet of trucks in a changing city? Or optimizing a truly complex manufacturing process with tons of variables?
Precisely. And another area where p-bits shine is in machine learning applications that deal with noisy or incomplete data. Because they naturally model uncertainty, they're well suited for building systems like Boltzmann machines, a type of neural network model that excels at learning complex probability distributions. You can build these directly using arrays of p-bits.
Boltzmann machines. I've definitely heard that term in the context of advanced AI research. So this could have a real impact on how we develop and train future AI models?
Definitely. AI often relies heavily on probabilistic reasoning, making decisions based on information that isn't 100% certain. P-bits are almost inherently built for that kind of task. They could provide a hardware-level acceleration for handling that inherent randomness, potentially making AI processing more efficient and perhaps even more robust to real-world, imperfect data.
Okay, so the upsides are notable. Potential for massive energy efficiency, ability to tackle challenging optimization problems, and boosts for AI capabilities. What about the challenges, though? Working with noise sounds inherently tricky. How do you make sure the results are reliable enough for practical use?
That's a key challenge, and it's a major area of active research. While the inherent noise is useful, you absolutely need to control it precisely. Ensuring controlled correlations between p-bits and maintaining reliable operation as you scale these systems up to solve larger, more complex problems are significant hurdles. Developers are exploring things like sophisticated calibration techniques and designing clever interaction patterns between p-bits to guide the computation towards the desired outcome, despite the randomness. Developing robust error correction mechanisms that work times the probabilistic nature of the system, rather than trying to eliminate the noise entirely, is critical. Some researchers are even looking at using machine learning itself to help manage and optimize the behavior of these stochastic fluctuations. A fascinating recursive idea.
Using AI to help the noise-based computing. I like that circularity. It feels very modern. So where do you realistically see this technology going in the near future? Are we going to replace all our traditional computers with p-bit machines?
Probably not entirely, at least not anytime soon. That seems unlikely. The most probable near-term future involves hybrid systems, combining classical CMOS logic for the deterministic, control, and input/output parts of computation with specialized p-bit arrays or coprocessors for the specific probabilistic and optimization tasks seems like the most cost-effective and practical roadmap. Think of it as a specialized accelerator or coprocessor for certain types of problems where its strengths are most relevant, rather than a wholesale replacement.
So your everyday laptop or smartphone still uses classical bits for general tasks, but specialized hardware inside for certain complex AI tasks or tough optimization problems could potentially use p-bits?
Exactly. This hybrid approach also makes adoption easier for industries and developers because it can integrate into existing hardware and software infrastructure. We're already seeing proposals for these kinds of hybrid designs, and companies are certainly exploring this space. Reports suggest companies like Intel and LG are reportedly investing in and working on scaling MTJ technology, which is a fundamental building block for implementing these p-bits.
That's a notable step. Seeing big industry players getting involved, it feels like probabilistic computing isn't necessarily trying to compete head-to-head with classical or even quantum computing across the board, but rather carving out its own distinct niche, offering a complementary approach for specific types of problems.
Definitely. Classical is the workhorse for most everyday deterministic jobs. Quantum is for those specific, highly complex problems where superposition and entanglement provide an advantage, assuming you can build and maintain the hardware. And probabilistic computing looks promising for problems that benefit from directly modeling uncertainty and are particularly sensitive to energy consumption. They each have their unique strengths and potential applications.
And the energy efficiency angle feels especially important right now, with growing concerns about the environmental impact of computation and large data centers. If this technology can make a noticeable difference there, that's a substantial positive outcome.
Agreed. Beyond the raw energy savings, faster, more efficient solutions to complex optimization problems can have broader societal benefits too, leading to better resource allocation, more efficient logistics in critical areas like healthcare or disaster relief, optimizing energy grids. The potential impact is significant, even if it's in specific areas.
It sounds like we're definitely just at the beginning of truly understanding and harnessing what this noise-based, probabilistic computing can do. More concrete case studies demonstrating real-world impact and commercial viability seem like the necessary next steps.
Absolutely. That's one area where the practical deployment and case studies are still catching up with the theoretical foundation and the progress on the underlying hardware like MTJs. We need more examples that clearly showcase the advantages in production environments. But the progress being made on the fundamental components and the architectural proposals are quite promising, indicating this is a field worth watching.
Well, this has been a thoroughly fascinating dive into the often counterintuitive world of qubits and thermodynamic computing. Leveraging noise to compute, who would have thought? Thanks for meticulously breaking it down for us, Mark.
Anytime, Jenny. It's a topic I find genuinely exciting and, frankly, a bit mind-bending in a good way. The idea that noise, something we usually try desperately to eliminate or suppress in technology, could actually be the key to developing more energy-efficient and powerful computational systems. It really makes you rethink things.
It certainly does. And for our listeners, we'll continue to keep an eye on this intriguing space and bring you updates as this technology evolves and more practical applications emerge. It will be interesting to see how these hybrid systems take shape. Thanks for tuning in to episode 207.
See you next time.